What is gravity?
You have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know. And by the way, this is called gravity.
What is gravity?
When you start asking, like, what it is, I don't know. This is called gravity.
So according to Neil, this is called gravity. But when you ask Neil what gravity is, he doesn't know. He doesn't know what it is. He just knows what it's called, right? So let me ask you this, Neil. What is this called? How come that didn't drop? What's that called? What is this called, Neil? Is that called anti-gravity? Is that what it's called? I'm not gonna ask you if it is anti-gravity, because you don't even know what gravity is. Apparently, a super scientist such as yourself and professional actor, you're only qualified to tell us what gravity is called. You're not qualified to tell us what it is. So again, Neely boy, how come I can't drop this helium balloon even when I try? Why is it rising? Is that anti-gravity, Neil? Is that what that's called? Because we all know you don't know what gravity is. So let me explain how density and buoyancy works, my friend. Well, Neil, since you don't know what gravity is, allow me to explain what density and buoyancy is. This microphone is more dense than the air in which surrounds it. A lot like the one you are holding, Neil. It's made of plastic and metal components. And the plastic and metal components of this microphone are more heavy than the air in which surrounds it. So therefore, when I drop it, it falls. No gravity, no attraction towards the theoretical center of the earth. No, no, no. This microphone is more dense than the air in which surrounds it. It won't fall until I pick it up and release it. When I choose to release it, it indeed does fall. Not because of gravity, but because the microphone is more dense than the air than which surrounds it. Now, on the flip side, what causes this to rise? Is this a case of anti-gravity, folks? Oh, no, no, no. This is a case of buoyancy. You see, there's helium inside this balloon. And even when I try to throw it down, it rises. How can the helium in this balloon overcome the force of gravity, which holds trillions of gallons of water stuck to a spinning ball? How can this helium rise and overpower the balloon? That's because the helium is less dense than the air in which surrounds it. So therefore, because of buoyancy, it rises. Yes, folks, there is no gravity and there is no anti-gravity. There is only density and buoyancy. Here it is once again, folks. Density and buoyancy. Density, buoyancy. 1, 2, 3. There you go, folks.
Buoyant force. What is buoyant force? Let us understand the meaning of the term buoyant force by performing simple experiments. Push a cork down into water taken in a trough. What do you observe? The cork rises up and comes up to the surface as soon as we release it. Now, to keep it beneath the surface of water, we have to exert a downward force. This means that the cork is experiencing an upward force. The upward force is due to the force exerted by the water. The downward force which we exert counters the upward force. This shows that when a body is partly or wholly immersed in a fluid, the fluid exerts an upward force on the body. The upward force experienced by a body when partially or wholly immersed in a fluid is called upthrust or buoyant force. The phenomenon responsible for this upthrust is called buoyancy. Let us perform a simple experiment to prove this. Suspend a body from the hook of a spring balance. Observe the reading. Now slowly immerse the object into a trough containing water. What do you observe? We observe that the spring balance is indicating a less weight as compared to the initial reading. Now slowly remove the object from the trough. We observe that the spring balance reading is slowly increasing. This shows that any object partially or wholly immersed in water or any fluid experiences an upward force called buoyant force, and this force is responsible for the apparent loss of weight of the body immersed in it.
That's interesting. 1 cubic centimeter of water has a mass of 1 gram. This is not a coincidence. If you research the history of the metric system, you will find that the first standard metric unit of mass, the gram, was defined as the mass of 1 cubic centimeter of water. The spectacle unfolding behind me here is a graphic demonstration of buoyant force. Amazingly, the buoyant force acting on a hot air balloon is able to lift a basket filled with passengers. This powerful force appears whenever an object is immersed in a fluid. Do you know what fluid this hot air balloon is immersed in? Remember that both liquids and gases are fluids. The fluid surrounding the balloon is air. Let's investigate the buoyant force in another fluid, water. This is a concrete block. This is a wood block, a softwood block, pine actually. I'm going to drop these 2 blocks into the water in the aquarium. One will sink, one will float. You probably have a prediction about what's going to happen. Let's find it. I suspect your prediction was correct, that the concrete block sinks. When I ask the question, why does the concrete block sink? The answer often is the concrete block is heavier than the wood block. We have to be careful with our vocabulary and understanding here. Consider a cruise ship. More buoyant force. This cruise ship behind me is in fact a huge hotel floating on the surface of the ocean. These huge ships can weigh over 50,000 tons. Despite this huge weight, cruise ships have no problem floating on the ocean. Whether an object sinks or floats is not determined by its weight, but by its density and the density of the fluid it is immersed in.